Hello guys, welcome back to my channel Gamma Di Gamma. So in the last video, I believe I talked about the introduction to tensors, and I said it was appropriate. It's way more convenient to choose a better coordinate system because tensors are basically system invariant. And let's talk about diagonalization in this video. Let's get started. Sort of express tensor sigma in a subscript summation convention. So sigma sub ij, it's the rank 2 tensor, e sub I hat tensor e sub j hat. And since this you can sigma remains sigma tensor in any coordinate system, you can express it in the prime coordinate system with sigma prime sub st e sub s prime hat e sub t prime hat. Now assume that sigma has only diagonal elements, and what I mean by this is, remember how tensors, rank 2 tensors could be represented by matrices. Now the assumption goes like this: I want the matrix to only have diagonal elements. So how I can do that is I can say have sigma tensor here, only diagonal entries, which means that both the subscripts are the same. And I want to dot this with E1 prime. Now this just becomes sigma sub ss prime e sub s prime Kronecker delta s1, because we always work with orthonormal systems, so Kronecker delta has to come up there. After contracting over subscripts, we have sigma sub 1 prime e sub 1 prime. Okay, so it's kind of evident that this diagonal basis, the prime basis, which is in this case the diagonal basis, causes no change in direction. Only possibly a change in magnitude, and for this magnitude change I'm going to do certain steps down here. So I'm going to define lambda 1 to be the component in this top line. So I have sigma tensor dotted with E1 prime is equal to lambda 1 E1 prime. I forgot the prime. So now this lambda 1 is what we call an eigenvalue, and E1 prime is what we call the eigenvector, corresponding to which we have an eigenvalue lambda 1. And believe me, this is the same language we used for the eigenvalue eigenvector video in linear algebra. Shouldn't be a surprise because we can represent rank 2 tensors as matrices, so this shouldn't come as a surprise that we can diagonalize or attempt to find eigenvalues and eigenvectors for that matrix. Please watch that video on eigenvalues and eigenvectors if you don't know what these things are. Now what we can do is define a unit tensor. And the way I'm going to do this is, it's like a weird one. I'm going to define it as Kronecker delta ij e sub I hat tensor e sub j hat. And if you basically, write down what each of these things are going to be, and at least a matrix representation, when I and j are equal, Kronecker delta is 1, and E1 tensor E1, so the first element is 1, everything else will be 0, and then we'll have 1 for 2 2 and 1 for 3 3. So this becomes just the identity matrix. So this shouldn't come as a surprise. Again, the property of this, at least in the world of tensors, is that if you dot the identity tensor with any tensor, you just get the same tensor itself. And again, this makes sense because it's the identity matrix. So identity matrix multiplied by any other matrix is just that matrix itself. So why is this useful? Because remember, we have this equation here. We have this equation here. Sigma tensor dotted with E1 prime is equal to lambda 1 E1 prime. I'm going to take lambda, I'm subtracting both sides with lambda 1 E1 prime to get sigma tensor minus lambda 1 along with the identity tensor dotted collectively with E1 prime, and this is equal to the 0 tensor, which is a matrix, which is the null matrix basically. Okay, we can just simplify this a little bit. Kronecker delta ij with a common subscript of E1 tensor EJ tensor dot E1 prime is equal to the 0 tensor. So we can do a little take the E1 on that side while we do this dot product. And here we're going to get, I believe, the transformation matrix between the prime and the unprimed. So A sub ij, this was covered in the last video, so please check that out if you haven't already. Now if you just look at the terms, forgetting the Cartesian basis vector, because that is really never 0, and we write this in a matrix, we have, say, sigma 1 1 minus lambda 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2 times lambda 1, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3 minus lambda 1, and then A11, A12, A13 is equal to, it's going to look like this. And now one way of satisfying this equation is if you have the same matrix and you let its determinant go to 0. Because the way I see this is like A11, A12, A13 should really not go to 0. They shouldn't be a trivial solution. So the only way of making this 0 if the columns of this matrix are linearly dependent. so that its null space is not trivial, its kernel is not trivial. And, the way to ensure that is to set the determinant to 0. That's the surest way to do that. So if you remember, this is the formula for finding the characteristic polynomial, at least when it came to linear algebra. Here it has a little, the meaning is a little different, but the way of finding it is the same, because we can represent rank 2 tensors with matrices. Now the funny thing about the transformation matrix as follows: if the E1 prime is equal to A1j EJ, and this is just because of matrix multiplication basically. And what we can do is we can dot both sides by, say, E1 prime, we get 1 here, A1j EJ dotted with E1 prime, we get A1j, which is like saying, say, A transpose A, and this is equal to 1. So this means that it's orthogonal matrix, or you can write it out this way: A11 squared plus A12 squared for this case, the one case, this is a more general statement, this is a more specific statement. Now one interesting thing is in the basis that's given by these prime basis vectors. So the primed basis sigma tensor is going to look like lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. And this is you can see this clearly by basically repeating these steps over here for like E1 prime, E2 prime and E3 prime. So this is the convenient basis that we were searching for, that basically motivated us to do all these steps. And typically these guys are Hermitian, so the conjugate transpose of these diagonal matrices are the same generally. So Hermitian means a conjugate transpose. In case it has imaginary entries, otherwise it's just going to be the transpose. Let me do one quick example before going on. Consider the stress tensor that will be given by 11 1 negative 1 0 negative 1 11 0 0 0 10. Now according to our equation that we made, we want the determinant of this guy to be 0. Again, it all stems from the fact that this matrix minus lambda times the identity acting on some vector in the prime system is 0, is null basically. If you solve this, if 10 minus lambda and 11 minus lambda squared minus 1, I'm skipping steps, so I have lambda 1 to be 12, lambda 2 and lambda 3 to be 10. So for lambda 1, if we plug this into this equation, we just get minus 1, minus 1, 0, minus 1, minus 1, 0, 0, 0, minus 2. Instead of having, say, E1 is basically the first column of this transformation matrix. So work with the null space, satisfy this equation. You get A11, A12, A13 to just be 1 over square root of 2, 1 minus 1, 0. Because remember, we need to normalize this vector here. So we need to basically divide by the norm of this entire vector. E1 prime therefore becomes 1 over square root of 2, E1 minus E2. This is the new basis expressed as a linear combination of the old basis. Now for lambda 2 equal to lambda 3 is equal to 10. What we can do is, we have a degeneracy, so two different eigenvectors give the same eigenvalue. So I'll just write it as it is first. We have A21, A22, A23. Well, it's actually pretty clear in this case what the second column of matrix A is going to be. It's going to be 1, 1, 0, but again normalize it. And this is for, say, one of them, and for the other it's pretty evident it's going to be 0, 0, 1, and you don't need to multiply or divide by anything because the last column was entirely made up of zeros. So this gives me E2 prime is just 1 over square root of 2 E1 plus E2. E3 prime is the same as E3. So the diagonalized tensor can be represented by 12, 0, 0, 0, 10, 0, 0, 0, 10 with the transformation matrix. Let's see. Well, 1 over root 2, negative 1 over root 2, 0, 1 over root 2, 1 over root 2, 0, 0, 0, 1. Yes. You can watch my video on basis transformation, like matrices in different bases, operators in different bases, to understand what's really going on. Or you can watch the eigenvalue eigenvector video. I think that's a better way to start learning about these things. Okay, let's talk about some tensors in or diagonalization in other systems. More like tensors in other systems, because it doesn't really make sense to talk about diagonalization. So we can always express the primed variables in terms of, say, curvilinear variables. The prime could be or are, in the basic cases we will consider, the Cartesian variables of x, y, z. But I'm just writing this down a little generally. So x1 prime can be x prime, because it's generally prime is generally Cartesian in this case at least, x2 prime is y prime is rho sine theta. This is a cylindrical system. x3 prime is z prime, which is just z. And well, we have vi prime is equal to the transformation matrix applied on vj. The position vector, differential position, is this guy basically, but this is equal to, using the formulas we derived using differential geometry, the scaling factor d q sub j hat, and we have also the relation a sub ij hj d q sub j. So well, this means dx sub I prime partial x sub I prime with respect to q1, sorry, with at expressed is in terms of q1, q2, q3 with respect to qj dqj. This is just chain rule going on here. So if you equate both sides, you get the relationship partial xi prime function of q1, q2, q3 divided by h sub j partial q sub j h sub j dq sub j. Just multiply divided by the scaling factor. This makes a sub ij. Now simply with respect to q sub j, and this matrix takes us from the curvilinear system to the primed system, which was the Cartesian. Now we can repeat similar steps and we can derive the relation that a sub ij is equal to, say, h sub I prime partial q sub I prime q1, q2, q3 with respect to h sub j partial q sub j. This converts from curvilinear to curvilinear, so from the q system to the q prime system. I mean, this is a general case. If you set, say, the scaling factor, the prime scaling factor to 1 and change from the q primes to x primes, you just get the top formula. So it's like a sanity check for us. And again, a similar way that you can define the matrix with the dot product. So q sub I prime dotted with q sub j hat for at least this case. Okay, so one important aspect of diagonalization, or at least a great example that will drive home the point, is the case of the inertia tensor. So for like a discrete case, consider a rigid body with n point masses. That's why I said discrete distribution. So the inertia tensor is something like this: I11, I12, I13, I21, I22, I23, I31, I32, I33. We define it as I sub ij is nothing but sum from k equals 1 to n m sub k magnitude of the position vector r sub k squared Kronecker delta ij minus x sub I of k y sub I of k. more like x sub j. Yes, that is a better notation here. And for a continuous distribution, we can have something like this: magnitude of r squared Kronecker delta ij xi xj dm, the differential mass element, because mass is now continuous, which we can also convert as a triple integral minus xi xj, the density function, and a differential volume element. Okay, the inertia tensor is important because if we have, say, formula for the angular momentum, we're going to have the inertia tensor. At least I'm differentiating the x and y now. I'm not using numbers anymore. I hope I don't miss any. I don't mess up the subscripts. And we have the angular velocity, at least the way I'm writing this formula. From rotational mechanics, this is L vector, the angular momentum vector, is equal to I applied to omega, and I is going to be a tensor because it depends on what axis we choose. And now each of these guys, Ixx, can be calculated from the formula above. So it's going to be sum k equals 1 to n y sub k squared plus z sub k squared, which can be written as this integral for a continuous distribution dm. Well, you do the same for like a yy, x sub k squared plus, I believe, z sub k squared, x squared plus z squared dm. Same thing for z. I'm just writing everything down so I just cover everything. Y sub k squared, which is nothing but x squared plus y squared integrated dm. And if you notice this formula or even the integral definition, you might notice that the moment of inertia tensor is actually symmetric with its with respect to its two subscripts. This is just sum from k equals 1 to n. We have x sub k, y sub k is integral negative xy dm, and then the other case yz zy this might come as a little surprise to the mathematicians in there, probably not for the engineers and the physicists, because this is a really fairly commonly used property. But the moment of inertia is sort of the measure of how sluggish the body is with respect to wanting to rotate or change its state of rotational motion. So assuming something has more moment of inertia about some axis, which means it's hard to rotate. I mean, if you provide some amount of torque, it'll rotate by less amount compared to some other axis. So the axes are important here. That's why it's probably makes sense to write the moment of inertia as a tensor and not just a scalar, like we have, like mass is a scalar in translational motion. The way to like make sense of all these guys is to look at this formula. The torque is moment of inertia and angular acceleration. So Ixy is if torque applied in the E sub x, how that affects the angular acceleration in the EY direction. So it's sort of a measure of like the unstability. This is again equal to yx because of symmetry. because you apply a torque in the x direction, but it can also rotate in the y direction, and that resistance to rotation is basically the magnitude of Ixy. These are basically the product moments of inertia, because Ixx is basically rotation or sluggishness to rotate purely about the x-axis. So you apply a torque in the x, and it also causes angular acceleration in the x. So it's for that. So when we diagonalize something like this this matrix representation for the tensor, what we're doing is we're finding a basis such that when you apply a torque in say Ey prime, it only affects angular acceleration in the same direction. So there's no effect of torque in y, causing effects in the x and z prime, for example. Apply in y, effects in y. Apply in x, effects in x prime. Didn't want to say x, but prime, because initially we may not have a diagonal matrix representation, and that's how diagonalization is empty, is pretty useful. Because if you have something like this, say I is 3, -1, 0, -1, 0, 3, 0, 0, 1. So it's a complicated system. Now again, the issue here I didn't address is it's not symmetric. So it's not symmetric. Take this as a really general case when some symmetry fails, but the point, this is just to prove a point. It's not a literal example, but if you diagonalize this, you get 1, 0, 0, 0, 2, 0, 0, 0, 4, which means you apply a torque in the x prime direction, it causes an angular acceleration of, say, which has basically the same amount as the applied torque, because there's a factor of 1 here. You apply torque in the y prime direction, it causes twice as much angular acceleration as the magnitude of the torque, because there's a 2 here. Apply torque in the z prime direction, the magnitude is 4 times for the angular acceleration than the magnitude of the torque. So in this way we can completely categorize a motion in this new basis, where the rotation is just a linear combination of rotations around these prime axes. So let me just write this out in a better way. I hope this video has been pretty clear to you guys. If not, you can read more about this. Okay, that's it, I guess. Please like, share, and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Di Gamma. And in the meantime, stay tuned for more content, and peace out.